So we've talked about contrast in the past, and contrast I've explained is just means different. Radiographic contrast means the difference between black and white. You're gonna need to pay attention to test questions whenever contrast is discussed, because again, there are two different types of contrast. There's radiographic contrast, and radiographic contrast is what you see on the image. Subject contrast is what provides the radiographic contrast. That's the difference between tissue types, tissue density, tissue thickness. All of that plays into subject density, and all of that in turn gives you your radiographic contrast. So it's difference between the dark images and the light images on your image on your monitor. So whenever we say that a radiograph exhibits high contrast, what we're saying is that it has the ability to record minute differences in tissue density. So a high contrast image would be one where you've got obvious density differences, where you can differentiate between things like bone and soft tissue, or bone and air, or air and soft tissue. It's very obvious. Where you have low contrast, it's not so obvious. Things like the psoas muscles versus a kidney versus the lower border of the liver. All those tissue types are similar, and since they're similar, the appearance on the radiographic image is also similar. So radiographic contrast is a product of the image receptor contrast, that is the contrast that's inherent in the image receptor system, including the computer algorithm in a digital world, and the subject contrast. So if you were to take an x-ray and process it under the wrong computer algorithm, it's going to change up your grayscale. What I mean by that is if you were to shoot a chest x-ray with a chest x-ray technique and you processed it under ribs, then your chest x-ray is going to look more like ribs. Ribs, what we want to see in ribs is higher subject contrast than what we do in chest x-ray. So even though you shot your chest x-ray with a chest x-ray technique, if you process it under ribs, and again, you can play with different things in clinicals to kind of bring this out and help you to understand this. But if you process it under a rib algorithm, it's going to look more like ribs. So that's basically the image receptor contrast is what's going to give you that. But even still, if you were to process, let's say you take KUB and you process it under a chest x-ray technique or a chest x-ray algorithm, which should give you a very steep H&D curve for a very high contrast image, you're still looking at very low subject contrast material. And you might improve the contrast to a degree, but it's not going to be as obvious as bone on air like what you're going to see at a chest x-ray. So both of those things play a part in the radiographic contrast, the image receptor and the subject contrast. So in the image receptor is mainly the lookup table, and the subject contrast is going to be your patient factors, those being thickness, usually because of an increase in soft tissue, density of the tissue, and the atomic number. Density and atomic number are not necessarily the same thing. The lung tissue itself is soft tissue filled with air. Once you collapse the lung tissue and get rid of some of that air, whenever you have a atelectasis and the lung collapses, then you get consolidation of that lung, and where the lung is actually increases in density because you're lacking the air. We tend to mistake pneumothorax. A few of y'all made this mistake on the last imaging test. we tend to confuse a pneumothorax and atelectasis. A pneumothorax and atelectasis are not the same thing. Atelectasis is the collapse of the lung caused by air inside the pleural space. The air inside the pleural space is your pneumothorax. So you get a loss of density in the pneumothorax and an increase in density in the atelectasis. So contrast, the difference in contrast or contrast as a difference looks like this. So what we have is low contrast. Things just look more homogeneous. They're more similar in appearance. So it's more of a overall gray in appearance. So we say contrast, high contrast is a image quality factor, and it is, but it can't be too high contrast. You can't shoot all your bones at, your bony tissue at 40 kVp. Because your mass would be so high that you could very much burn out the soft tissue detail that you need to see, so that all you see is bone and not bone. And that's kind of what we have going on over here. The subject contrast is too high, so we need a balance between high contrast and contrast that's not too high. This is just too low, and it's milky in appearance. This is too black and white. We need a balance between the two. So how KVP controls that is through penetration. As KVP goes up, more tissue is penetrated more similarly across the board, especially whenever mass is manipulated to control the image receptor exposure. So at low KVP, you only penetrate through a certain number of tissue types. So I've got 3 different things here, and all of these were pulled from the internet in a search of KVP and contrast. So what we have is with low KVP on a step wedge being like what you've seen in class, a piece of aluminum or a thick piece of acrylic that just goes up kind of in a stair-step fashion. So what we've got here is a step wedge that utilizes low KVP, and we've got very dark density here and a very light density there. And if we count the light and the dark and all the steps in between, all we see is 1, 2, 3, 4, 5, 6, 7 steps. So we have a narrow range of contrast, so a short scale contrast. As opposed to a higher KVP, you can barely make out the difference between these two, but it's there. And these two are very similar, but they're obviously different. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got a wider range of contrast because of the higher KVP. We penetrated through more of the step wedge than what we would have otherwise at lower KVP. So this end of the step wedge would represent the thicker or the fatter portion of that piece of aluminum. This would be the thinner portion where x-rays got through really pretty easily, and they didn't get through it all up here. So as KVP goes up, we can penetrate more of those steps, and our contrast, our scale of contrast, is broadened. So high KVP gives us low contrast. Low contrast means we got a wide range of densities. So low contrast, wide range of densities, wide grayscale. High contrast, narrow grayscale. High latitude, low latitude. So looking over here, you see it going up incrementally. At 40 kVp, we only penetrated to here. At 50 kVp, we penetrated to about here. It doesn't really look like there's a whole lot of change at 60 kVp, but 70 kVp, you start to see some densities. 80, 90, and 100, you've penetrated every single one of them. So at 40 kVp, it almost looks like we only have 1, 2, 3, 4, 5, 6, 7 steps. And at 100 kVp, you can see each one distinctly different than the other. Narrow contrast, wide contrast, high latitude, low latitude, long scale, short scale. So how we manipulate contrast in a digital world really is by changing your lookup tables. You change the lookup table and you change the shape of the H and D curve that's associated with it. So if you change, again, from a chest x-ray to a ribs lookup table, then you're going to change the dynamics of your x-ray. If you apply a chest x-ray lookup table to ribs, it's going to look like a chest x-ray. If you apply a ribs lookup table to a chest x-ray, it's going to look like ribs. So what you tell your computer you want it to look like is going to apply an H&D curve to your image, to your range of exposures that you created, to try to fit it within a window that would describe the exam that you told it that you were shooting. But you can influence it with KVP. I say influence when you're reading a test question, and the test question asks you what controls your contrast in a digital world. Well, what controls your contrast in a digital world is your lookup table. But if the question asks you what can the technologist use to control contrast, or what technique, what technical factor can the technologist use to control contrast, that's your KVP. This really is a throwback to screens and films. The registry still says that KVP controls your contrast, and it really doesn't. And that's another change I expect to see probably sooner than manipulating KVP as a technical factor rather than mass. I really expect them to drop KVP from describing the things that really control your contrast, your radiographic contrast. Still does affect your differential absorption. So in theory, the way that we get to radiographic contrast through the remnant beam is still valid, but again, we apply a lookup table that doesn't match what we expect to see with KVP, and we can kind of, in a way, override the KVP and its effect on contrast. So really, when we're talking about contrast, we're talking about visibility of recorded detail. Remember, we got two different types of detail. We got spatial resolution and we got contrast resolution. So that's sharpness of recorded detail and visibility of recorded detail. So visibility of recorded detail can be manipulated by KVP because KVP creates scatter. As the KVP goes up, scatter creation increases. So when we're talking about visibility of recorded detail, we're talking about what might cover up your actual sharpness recorded detail. And most of the time, that's going to be scatter radiation. So as KVP goes up, scatter is created and penetrated through the patient at a higher rate. More of the remnant beam is dominated by scatter radiation as opposed to penetration without any scatter in it. And as a result, we can cover up the visibility of recorded detail. So we want to use the proper KVP. We can get too high with our KVP and cover up our detail. Our visibility goes down. If we're shooting low contrast tissue, like primarily soft tissue, then we're going to create a lot of scatter radiation regardless of what the KVP is. And increasing the KVP only makes things worse. So if we're shooting through a tissue type that creates a lot of scatter, soft tissue, abdomen, really pretty much anything that's knee size or shoulder size or above, we need to use a grid because we create a lot of scatter radiation. So the purpose for a grid is to clean up scatter radiation after it's created. Beam restriction, on the other hand, and we'll talk about both of these in the next section, beam restriction prevents scatter from being created. Tissue that's that is not irradiated doesn't create scatter. So the more you collimate, as you increase collimation, you make your field size smaller, then you reduce the likelihood of creating scatter radiation. Actually, you reduce the scatter that would be created in a larger field size. So the more we collimate, the smaller we make our field, the less scatter radiation we create. So what we want to do is use the proper KVP. We want to use a grid where appropriate and collimate anytime that we can use beam restriction. And in that way, we don't create more scatter with a higher KVP. We absorb the scatter that is created in tissues where grid use is appropriate. And we also prevent scatter from being created in a portion of the anatomy that just didn't need to be exposed. So again, we got a throwback to the H&D curve here. We got two axes. We got the density axis, which is a horizontal axis. The exposure axis is the vertical axis. Average gradient is a measure of contrast, and it's calculated as rise over run, and that's how you calculate a lot of different things. Rise over run is slope of a hill, slope of a roof. That is how high something goes over how far out it goes. So if your roof line goes up 1 foot for every foot that it goes from left to right, then your roof line goes up at a 45-degree angle. All right, so a 45-degree angle would be a very low contrast. Thinking back to the H&D curve, 45-degree angle would be a very low contrast H&D curve. Most of our image receptors are going to be much higher than that, so it's going to be much steeper than that. So in that, 1 unit of exposure gives us more than 1 unit of density. So it goes from black to white very rapidly. Rise over run being greater than 1 tells us that we've got a very high contrast image. If it's a very shallow average gradient, then our rise over run is less than 1, and what we're looking at is something that's very low contrast. So latitude, again, is inversely related to contrast. As latitude goes up, contrast goes down. As latitude increases, contrast decreases. Remember, inversely proportional or inversely related means that as one thing goes up, another thing goes down by even amounts. So latitude and grayscale are really the same thing. Since contrast and grayscale are inversely proportional and opposite from each other, then latitude and grayscale are the same thing. So again, your technical factor that's going to control your latitude is the KVP. You'll hear latitude referred to in two different ways. Grayscale being latitude, but also techniques that are high versus low latitude. And what we're talking about there is as KVP goes up, the theory behind it is that we get better, or I'm sorry, as KVP goes up, we get lower contrast. But going back up to this here, it also refers to how forgiving the technique is. If you use a high KVP on something, pick your anatomy, pick whatever absorber you're shooting, a very high KVP will penetrate where low KVP won't. So let's say you're trying to penetrate this step on the step wedge right there. If you reduce below 40 KVP, you're probably not going to penetrate anything through that particular step. Whereas if you decrease from 100 KVP by 10%, you're still going to penetrate through it. You're still going to be okay. If you increase your KVP, you're still going to be okay. Whereas at 40 KVP, you're just at the threshold of being able to penetrate certain steps on the step wedge. So KVP is not only describes the latitude and the contrast, but also the latitude in your ability to penetrate different tissues. and the latitude that you're afforded in selecting your technique. So how does this apply now? In CR and DR world, again, your lookup table is a stored histogram inside of your computer. So when you make an exposure, you create a histogram. We don't call your histogram the lookup table. The lookup table is a stored histogram inside of the computer. So as you make an exposure, you create a histogram that the computer is going to compare to the stored histogram. The stored histogram is lookup table. And if you shot with your KVP being slightly too low, then the computer algorithm, providing you penetrated through the structures, it can manipulate those density levels to make your histogram look like the lookup table. So if you shoot with such a low KVP, going back up to our pictures of the step wedge, that you don't penetrate through all the tissue types, then you feed your computer something that it can't handle. The old electronics saying that garbage in equals garbage out applies here. If your technique is somewhere in the ballpark of what the range of exposures that the lookup table would recognize as being similar to itself, then your lookup table and your computer algorithm and your computer system will adjust the density and contrast to your image to make it look like the image stored in the computer. If, on the other hand, the image stored in the computer looks like this, and you feed it this, you're going to get what you call a histogram analysis failure. It can't figure out how to make this look like this. It's going to take these few densities and it's going to spread them out, and you're going to be inadequate.